So let me see, did this do what it... No, this is not.
You need to turn it on. There's a thing on the side.
So,
The people could also make it a little bit more focused, or
what's it?
my eye, so it looks a little bit blurry.
Yeah, that's all better.
There he goes. One less direct before.
Okay, so I'm going to talk in particular about using QCD at what's called the intensity frontier. And so I'll start by talking about the intensity frontier. So this is the laser, okay. And then, as you'll see, at the intensity frontier, nuclear physics actually becomes an important player in particle physics. And so I'll spend time talking about the connection between nuclear physics and the underlying theory of QCD. And then I'll talk about sort of the calculations I really want to highlight, which are calculations of nuclear matrix elements in QCD that are relevant for the intensity frontier. So let me start with the intensity frontier. And really, by definition, what this is really trying to look for new physics by looking for quantum effects. So instead of going to very high energies and trying to produce new particles directly on shell, what you try and look for is their effects through quantum loops. So it means doing very precise experiments, and experiments that are really sensitive to the very rarest interactions of the standard model, things that approximate symmetries, if the symmetry was exact, would not be there, but because it's not an exact symmetry, there are contributions. And also looking for effects where there is really no standard model contribution. And so this is, at least in the United States, this is a major focus of the high energy physics experimental program for the next decade. So with the energy frontier really being at CERN, the kind of next generation of experiments in the US are really probing this intensity frontier. So the kind of experiments these are direct detection experiments looking for dark matter, for a whole bunch of experiments aimed at neutrino physics, things like charged lepton flavor violation experiments, proton decay, anti-neutron oscillations, and other things that, such as these, that in the standard model don't happen, but in principle can. Okay, dark matter is one of these. Dark matter searches is one of these. So how do we look for dark matter? Well, there's really three ways people look for it. So you can look astronomically to see signals of dark matter annihilating and producing photons. You can look for it by directly trying to produce it at colliders, or you can do what's called direct detection, which is really waiting for dark matter to pass by us and interact with a nucleus in a detector. So you have some big detector full of nuclei, and then something comes in and knocks one of them. And it really is what these experiments do is look for single nuclear recoils in a big tank of.
The atoms are not escaped.
No, not with the person.
This is not going to happen.
Right. Yes. So yeah, these type of experiments, not to this scale, are being done at a range of different places in the world at the moment. And so what you're really looking for is that interaction with the nucleus. And if you see it or you don't see it, it lets you, well, if you don't see it, it lets you place a bound on how likely those interactions were. Right? So, and so here, for example, is the bound that came from Lux last year. So this is the cross-section versus energy in a particular model for what dark matter is, and this region here above this is ruled out by their non-observation of these events. So this is a pretty complicated thing to do, and so the rate at which you see things, it depends really on beyond the standard model of physics, so what are the dark matter properties and its dynamics, and also on kind of just where in the universe dark matter is it sitting right on top of us or is it not? But it also depends on the probability of, given a dark matter particle passing through this detector, what the probability of interaction with the nucleus is. And fundamentally that really corresponds to the nuclear matrix element of some current in the standard model. Okay. So that's essentially, yeah, so we're looking for nuclear matrix elements of some exchange current. There's another class of experiments which are, in terms of their standard model contributions, are similar. So these are charged lepton flavor violation experiments, in particular the mu to E experiment. So in this experiment, which is shown, this is going to happen in the next 5 years, this is shown down here, and basically you have a proton beam come in here, hit a target, produce muons that then stop in this aluminium target and actually get captured around an aluminium nucleus. And because it's a muon, it goes into a very small orbit, and so it's essentially within the the matter distribution of the nucleus itself, this muonic orbit. And eventually, what you hope happens is that you undergo a charged lepton number violating process where the muon converts to an electron. Okay, and then the rest of this is to see these electrons and really characterize them. Now, because this is happening within the nucleus, it's really a nuclear matrix element of a set of different operators that allow this process to happen. Okay, and in the standard model with neutrino masses, this does happen through the mass oscillation in the neutrino sector, but it's at the level of a cross section of about 10 to the minus 54, so it's never going to be seen. Okay. But in models beyond the standard model, this happens with a much higher probability, and so this experiment actually hopes to see it. But again, what it needs is understanding of what the matrix elements of the operators that are relevant is within a nucleus. Okay. Now, in both of these cases, I should actually say that if you see an event in a dark matter detector, or you see this mu to E conversion experiment above the background, then okay, you're probably going to get a Nobel Prize. Okay, so a positive signal is very nice because you don't need to know the standard model physics to a great degree to say you saw something. But if you want to understand what it is you saw, then you need to really go and understand the standard model contributions. And that means you need to know these nuclear matrix elements.
Yeah, I mean, but for this mu to E, it's not the mass of every extension of standard model violates flavor.
Sorry, it's not?
It's not the mass of every extension of standard model. You can also make the central standard model that doesn't do that.
Yes.
So,
Yeah. Yeah,
it's not a foolproof theorem that you must see it. Right?
No, certainly
And
not.
even if you don't see it, you physically still be there.
Yep.
It just doesn't happen there.
That's right.
So,
Sure.
I mean, I appreciate the effort one to see. One should look for everything one can look, but
Right.
it's no theorem that says they should be there. There's no physics.
Right. And on the scale of things, this is actually a pretty cheap experiment.
Yeah,
So it's-
I understand the logic, but it's not the mass of every extension of standard model.
No.
Not quantum. If one is conservative, typically make extension that deviate as least as possible from the standard model
Right.
nowadays.
Yep.
You can do that, but at your own risk.
Right.
It's excessive.
But somehow if you unify, like for example, like at a higher scale, there must be, yeah, but you have to put them together at some point. I mean, why not?
And the neutrino, I mean, I see, we don't say correctly, the neutrino varies, but the interactions are very small already in the standard model. So
Right.
there's absolutely no reason to have that, except for the fact it's an experiment to look for it, which is a different way. So it's the logic is the other way around. Since you have an experiment that's looking for it, Curious are going to make experiment models that actually can be searched for.
Right.
So the logic is a little bit twisted.
What is the sensitivity of this experiment for the conversion ratio?
So to about a cross section of about, I think it's about 10 to the minus 19. The standard model is 10 to the minus
There is
54.
at least for the one who's higher than the current bound.
Sorry? Yeah, so this is going to, so I mean there are other there's mu to E gamma experiments that also look at the same kind of physics, and so yeah, this experiment is going to be about 3 orders of magnitude more sensitive than previous generations.
And I heard that there is also a proposal of using the titanium as the candidate, right?
So aluminium is going to be used first.
But then
So actually, so this is quite. So there's a lot of reasons for why you want to choose why experimentalists choose targets. Some of them make sense to theorists and some of them don't. If you are a theorist and you want to actually understand this, then you really need to understand the nuclear physics in this particular experiment, and so you would do it with a whole range of targets. So in fact, one of the things that they want to do is use different targets eventually. Does that answer your question? Yeah, okay. Okay, so yeah, so my basic point is in these experiments, okay, if you see a signal, that's great, but if you actually want to understand what's going on, then you need to understand the standard model. And this is also relevant for when you're designing an experiment, right? Because if you find that the standard model tells you that you shouldn't see this with this particular, let me not say that. So actually just in understanding what size of experiment you need to build for these dark matter detectors, for example. This is something where knowing what the cross-sections are would be useful. Okay. So another kind of piece of this intensity frontier is really neutrino physics. So here you're looking for really disentangling neutrino oscillations better than we know them so far. For example, looking for CP violation in the neutrino sector, trying to understand the mass hierarchy, whether you have two light neutrinos and a heavy one, or a light one and two heavier ones. So long baseline neutrino accelerator experiments are really kind of the frontier for doing this. And so again, the targets to be used in neutrino detectors over the years at least have been many, and they're all nuclei. So they range from carbon, argon is a particularly common one, and include things like steel, which is a really complicated target if you want to think about the nuclear physics of it. Okay, but if you go to these experiments and want to extract oscillation parameters, what you need to know in this experiment is you basically have a source that produces a neutrino beam that is hard to characterize because they're neutrinos. And that goes through the Earth for 1,000 kilometers or so, and then it hits your detector. And its interaction with the detector is kind of complicated. So something like this might happen. So here's the neutrino coming in. You have a weak interaction, so you get an outgoing charged lepton, which is nice, you can measure that. But then this interacts with a nucleus, and perhaps one of the nucleons inside the nucleus gets excited to a delta resonance that then decays to a nucleon that comes out, so maybe this is a charged proton, and a pion, and that pion gets reabsorbed. And you've got to understand all of the kinematics of this interaction in order to characterize what the beam that you used was. So this depends on a lot on nuclear physics. So it depends on, firstly, the axial form factors of a nucleus, but also the transition form factors. So how this process here is really a transition from kind of the ground state to an excited state of this nucleus. And at higher energies, it also depends on deep inelastic scattering of neutrinos on a nuclear target. And in fact, the current knowledge is really one of the most significant uncertainties in the proposed LBNE or LBNF experiments in terms of determination of the oscillation parameters. So this is a plot that you can see, 3 colored curves here. These correspond to, for the measured sine squared theta 1,3 for 3 different CP violating phases. I think it's pi over 2, 0, and minus pi over 2, so the top 3 curves. And what you're trying to do in this experiment is distinguish between those 3 curves here, right? And so the typical energy is in this range here, so you're really looking for a difference of those 3 curves here. And the black region actually corresponds to the, in some way, to the uncertainty coming from the uncertainty in the nuclear cross-sections. And so what you need to do is narrow that dark region down such that you can really say you can distinguish between those 3 curves. Okay? And you can see at the moment there's no chance in hell you're going to do that. Okay? So you need to improve our determination of the energy. You need it to go, instead of at the order of, it's not really a very good plot showing this, but the energy resolution needs to improve by about an order of magnitude in order for this to work. Luckily, this experiment is not going to happen until 2025, so we've got some time to do that. Okay. All right, one more example of the intensity frontier, and this is neutrino-less double beta decay. So as you may know, certain nuclei are such that single beta decay is not allowed. So this is a plot of the proton number for the A equals 76 nuclei, labeled by their chemical label, and this is the binding of that system. Okay, so typically they like to go to, things like to go to lower energy, so this one can decay here by changing its proton number by 1, so this is just a single beta decay. But some of them, such as down here, so germanium, it can't do a single beta decay because the next isotope is less bound. But it can do a double beta decay, so it can change its proton number by 2. Okay, so double beta decay is allowed and has been seen. So there's about 10 different nuclei where it's been observed, or maybe a few more than that, and 10 other ones where it's observed with some high confidence. And it's a pretty rare process, so the typical half-life by this decay is about 10 to the 19 years. So you have to look at a lot of this stuff to see it happen. Even less likely is neutrino-less double beta decay. And so this happens if neutrinos are Majorana fermions. So a Majorana fermion particle and an antiparticle are the same thing, so you can have this process here happen. So here's neutrino turns to an antineutrino, and then that works. So there's two. So in this process, this is just normal double beta decay. You've got two electrons and 2 neutrinos coming out. Here, the neutrinos do this, or do this. It's sort of shown better down here. You can't really see this one. And you get the double beta decay process without any outgoing neutrinos. Okay? That's if neutrinos are Majorana, which we don't know. This process is bounded so far. It hasn't been seen, so the bound's about 10 to the 25 years for the lifetime. So, all right. So in order to determine whether we should have seen something, we need to know how likely it would be, how big a experiment we need to do in order to see it. And so the half-life really depends on this contribution here, the matrix element of these 2 weak currents in a nucleus. Okay? And here's the expression for the half-life, there's the matrix element we need. Okay, and this is really a nuclear matrix element. These are all quite heavy nuclei.
I'm sorry, that you can calculate it by checking the one with 2 electrons, right? Experimentally. I mean, the 2 processes, that will better decay without the emission of 2 neutrinos.
Yep.
The one with the emission of 2 neutrinos, that's the same.
They differ because
I mean, in the final state I understand, but in the initial state,
so they differ because of the kinematics of what the W's are doing, right? So up here, there's no integration over this momentum around here. So you certainly can constrain the nuclear models somewhat doing this.
they should be related, right?
They are
Kinematically related.
They are related. You don't know everything about it. So actually, the next slide. So these are these matrix elements for various different nuclei, and the colours correspond to a whole bunch of different nuclear physics models for how to calculate. So the shell model, interacting boson model, random phase approximation, kind of the state of the art of nuclear physics, all of which will actually are basically constructed to agree on this process. Okay? And you can see that they vary quite significantly in what they predict for this. So there's a spread, and in fact you might ask whether this spread is really representative of the true uncertainty of these matrix elements, and I think even the people that do these calculations say that it's probably not. Right? They're not particularly well controlled. But that actually matters because if you are off by, let's say, a factor of 3 in these matrix elements, that means, and the matrix element is actually 3 times smaller than what you hope it is, that means that your detector needs to be 10 times bigger in order to see the same cross-section. Okay? And that turns into 10 times as much money that you need to build the detector.
What's the scale linearly, is that? I doubt it.
No, it's probably worse than that. Okay, so I want to spend a little bit of time talking about the uncertainties in the nuclear physics of these things, and just give an example of how well we actually know these matrix elements. And so the answer is we don't know them that well. And so an example is looking at Gamow-Teller transitions. So these are axial vector isospin changing transitions. So these are basically the axial vector piece of the weak interaction. And so these are nice because they're well measured for a large range of nuclei. There are many nuclear structure groups that try and calculate these matrix elements. And in these nuclei, they do very well at describing the spectrum of these nuclei. So they're sort of the best controlled place to try and do nuclear structure. But the matrix elements of Gamow-Teller transitions are actually off by about 30%. So here, this is the experimental matrix element versus the theoretical prediction for it. And so if there was agreement, there should be a line with slope 1. And then these are a range of different nuclei. This line here has a slope of about 0.7. And that's telling you you're getting the nuclear physics wrong at about 30% level in this kind of best case scenario. So what people do is really correct for this. They find this, so they add in a new effect, which is changing the axial charge of a proton and a neutron inside a nucleus, okay? Which is a pretty ad hoc thing to do. So that's what's done.
I mean, is enough rescaling, universal rescaling to get a better fit, or it will depend by case by case?
So, yeah, at the level this is known, yes it does. I mean, this works, but you know that fundamentally that's not the right thing to do.
Right, it's not a conserved charge.
Right, yeah, so you're doing things are just, this is very ad hoc. And what I want to talk about is how to do it better. One more example is looking at kind of high energy physics. So this is the EMC effect. So this is looking at deep inelastic scattering, electron scattering in this case, and on a nuclear target, and this is iron in particular. So this is a very famous experiment called by the European muon collaboration in about 1983. They measured the ratio of the cross-section in deep inelastic scattering of iron to that in deuterium, which is almost like knowing in the proton. And what they measured as a function of Bjorken X, so this is the momentum fraction carried by the struck quark inside the target. They measured this ratio and found this big deviation from 1. Okay? And this is really telling you that proton structure is modified in a nuclear environment, which from a standard model point of view is a pretty obvious thing that should happen. But it's certainly this, even after now more than 30 years, this is only really understood at kind of a phenomenological level. There's no ab initio description of why this happens and how it happens. Okay. So I think there is really a definitive need to really look at nuclear matrix elements in precision in the coming years. In order to do this with precision, because we're really trying to look for physics beyond the standard model at the intensity frontier, you have to base these calculations on the standard model, because you want to look for deviations from it. And you have to really have fully quantified uncertainties. And part of the problem with the nuclear models that I showed you earlier is there's no way to quantify the uncertainties in them. They're just ad hoc. And there's really now a time frame in which these things are needed. And currently we're a long way from doing this. And if you think about flavor physics in the 90s, where the B factories were coming online, there was really a big push to understand flavor physics, the QCD contributions to flavor physics at high precision. And I think in the next 10 years or so, this is going to happen in the field of nuclear physics. You really need to understand these things at high precision. And so my goal is to try and start developing the appropriate tools to do this. All right. So let me now talk about QCD. So nuclear physics is standard model physics. Okay? And we know how to deal with the standard model. Okay, we've written down its Lagrangian, so we should just be able to calculate this. So we should be able to take lattice Qcd and do everything using that. At least in principle that's true. In practice this is a very difficult problem. It's difficult because we're really in this non-perturbative domain, so you have to use lattice methods. And it's difficult for physical reasons because nuclear physics really occurs at multiple different scales. Right? So if you think about the standard model, you really just get in the strong interaction sector, you just get to talk about lambda Qcd, quark masses. These give you hadron masses. Well, you also have the top part mass up here, but you also get these very different scales occurring. Here is the energy of lead, right? And this is really the same physics that gives you the proton. So Qcd produces bound states over many orders of magnitude. If you look at nuclei, there's another problem in that this is one particular nucleus, germanium-73, and now instead of being in GeV, this is now a plot in KeV of the excitation levels of germanium nucleus. And you see that there are very, very tiny excitations, right? And so trying to describe physics that goes from the scale of 200 GeV, where the lead nucleus ground state is, to its excitations, which are measured in KeV, is going to be a challenging task. Nevertheless, our goal is to try and develop the tools such that we can do this with some level of control precision and really control of our uncertainties. So this is not something that I think you can do from Qcd directly. You really have to exploit the fact that nuclear physics has effective degrees of freedom that are nucleons inside a nucleus. So really the way to do this is to think about it in kind of a hierarchical setting. So down here, for small atomic number, we can do Qcd calculations. Okay? And with those, you can really constrain effective field theory, which is what EFT stands for, effective field theory methods that allow you to make predictions in the kind of light to medium range nuclear realm. And then, in order to go to large nuclei, so for example xenon, which is one of the primary things used in dark matter direct detections, I think at the moment these effective field theory based methods are also not going to be able to go all the way to those large nuclei, so you have to use those to then constrain further layers of approximation. But if you can do this, and you can really constrain these matchings between these different calculation methods, then you can hope to have really a prediction for a matrix element in xenon that is fundamentally based on understanding of Qcd. Okay? So I'm certainly not an expert on this stuff, and today I'm really going to focus on how we do the first step, how we look at the nuclear physics within Qcd. Okay, so this is going to be using lattice techniques. So from the point of view of today's talk, lattice Qcd is really just a way of dealing with the quarks and gluons. I'm not going to spend a lot of time talking about lattice Qcd. As I was saying earlier, we formulate a problem measuring some observable O in terms of a functional integral over quark and gluon degrees of freedom. Then we discretize the system, as I showed down here. And then this functional integral becomes a finite but large number of degree of freedom ordinary integral. Okay? And we can integrate it via doing importance sampling because of this exponential damping of large action configurations. And the real challenge in lattice Qcd is understanding what you've done in doing these approximations and taking them away. I do need one little piece of lattice Qcd technology, and that is how do we do spectroscopy? Okay, so how do I measure the mass of a proton? And really it's all shown in this picture down here. So I've got space, all three space directions going up here, and I've got my Euclidean time direction going along here. What we do is at some time we put in a source that has the quantum numbers of a proton. So it has two up quarks and a down quark. That looks something like a proton. It's certainly not the eigenstate of the theory, but it's got the right quantum numbers. Okay? And what that does is in fact excite all eigenstates with those quantum numbers. So it excites the proton, it excites some radial excitations of the proton, and those all propagate away from this point. It's kind of like if you drop a pebble in a pond, you get radiating waves, right? This is basically what happens here. And then at some time, some late Euclidean time, we remove those quantum numbers. And so then we look at the correlation of those 2 points. And you can show that this correlation, just as a function of the time separation of those points, is going to be given by a sum over all eigenstates with the right quantum numbers of exponentially falling factors. And the coefficients in these exponentials are the energies of the states of those quantum numbers. And what we're really after is the ground state of the system, so the mass of the proton. So what we do, because of the exponential damping, is just go to very late Euclidean time, where the signal just goes like this. And then, in order to really pull out just the energy, we can take this correlator at time t and time t plus 1, take a ratio, and then take a logarithm. The ratio kills the z factors, and the logarithm just gives us this E0. So at late times, this, what's called an effective mass, should go to a constant, and that constant is characterized as the ground state energy of the system. And so over here is an example of four different choices of what these blobs are, so these things with the quantum numbers of the proton, all going to give you a flat behavior at late times, which is measurement of the energy of this system. Okay, so that's how we do spectroscopy, and that's really all I'll need today. So people have been doing lattice QCD for 30 plus years. By now, we actually can reproduce the ground state spectrum of hadrons to a pretty good degree. So this is a summary plot from Andreas Kornfeld that compares lattice calculations, which are the colored points, all of which have been extrapolated to the continuum and dealt with the issues of finite volume, compared with experiment, which are the solid lines here. So these are the light hadrons here, so pions, rhos, nucleons, lambdas, sigmas, and up here are various heavy quark systems which have been shifted down to fit on the same plot. And you see that the QCD calculations are all in agreement with the experimental determinations of this. And this is no mean feat, because this is really telling you that the strong interaction, which we know, historically we've known agrees with the experiment at very high energy, also agrees with the experiment at low energy. Right? So it's pretty important that this is now known. But we can also use this so we can make predictions. So this is a recent paper I was involved in, looking at not just the light and strange systems, but also thinking about systems with bottom and charm quarks in them. And so this is in fact a complete scan of all possible ground state hadrons involving up to 3 bottom quarks or 3 charm quarks, which experimentally you might not be surprised to know we haven't seen all of these hadrons. But it's a place where we can use QCD to make predictions. And so these indeed are predictions for what the masses of these states should be. Okay.
So if you're doing that on the left, some
Yes.
of these might be pretty broad.
No, these ones, well, no, these ones are really,
how do you know they're stable?
they're stable under the strong interaction, the ones we're looking at here. Most of them, so, well, no, sorry, the lowest one in each column, no. Some of them are not, so the ones with the
They
star
can
on
decay,
them,
right?
these can decay strongly, some of them. But a lot of them are the lightest state with the right flavor quantum numbers. Okay. So we can do better than this. So we can actually do calculations now in the standard model as a whole. So, well, at least without the electroweak sector, So this is now a calculation that appeared last year of the mass splittings between, for example, the proton and the neutron. And so these get important contributions from the strong interaction, from the difference in masses of the up and down quarks, but also from QED. Right? And so this is something where you need to do a calculation that's not just a QCD calculation, but you need to do QCD plus QED. And this has been done, and you see the level of precision, so the red points correspond to the lattice QCD plus QED calculation. So you're getting this splitting, which is measured in MEV with an uncertainty of well, maybe a couple of hundred keV. And for the neutron-proton, we know this experimental number to much higher precision, but for something like the splitting between the sigma minus and cascade minus and cascade zero baryon, this is something where experimentally we know it with only this larger error band here, which you can barely see, and in fact the QCD plus QED prediction is more precise in this case. Okay, so this is really going to be quite a precision tool. Okay, so this is all talking about...
Sorry, so the masses of the up and down quark have been put at the Carrot limit?
No, they're tuned to the physical.
So 4 and 7.
Actually, no, this is not quite right. So the masses used in the calculation were heavier than physical, but
the difference is the correct one.
Right.
So the cheat is in the difference. I mean, the thing is that the difference between up and down is the physical one.
So,
but the actual value of the mass is much larger.
Not much larger. I don't remember the exact details of what the lattice mass used in the calculations were, and they study it as a function of the mass splitting, in fact.
I mean, this is an effort to do the splitting technically, so I would
Yes.
say it's okay to have it to the bulk of the mass, not to be the physical
So
one.
yeah, you certainly know this splitting to a much higher precision than you know the mass of the proton in this calculation.
Exactly. I see. So the absolute value I shouldn't trust it of the masses, but the difference.
No, I think you should trust the absolute value as well, but the uncertainty will be much larger.
Okay. Good.
Okay, so, all right, so the single hadron sector, so mesons and single baryons is under pretty good control, I think. So now we can come back to nuclear physics and ask, well, can we do the same thing? And in principle we can. The same techniques will in fact give us the mass of lead, except we would need to wait an extremely long time for all of these tiny excitations to die out before we could measure the ground state energy. And there are in fact more problems. So there's two problems that I want to spend a little bit of time talking about. One of them is noise. So because we're sampling this functional integral stochastically, you have to worry about how our measurements behave statistically. And in fact, the uncertainty that we get is going to naively grow exponentially with the atomic number of the system we're interested in. Another problem is the way in which we tie together these quark creation and annihilation operators becomes much more complex, because the smallest kind of system, well, I'll come back to this. And in fact, this grows factorially, which is essentially exponentially. So let's first look at the noise. So we're trying to do importance sampling. So we have this factor here that we think of as a probability measure in this integration. And we sample according to that probability measure. And that means our correlators are determined statistically. So we're going to look at a correlator where we put in 3 quarks and annihilate 3 quarks over here. And from that we get a signal that goes like e to the minus mass of the proton t at late times. Okay? But if you've got a correlator C whose expectation value goes like this, the variance is determined by the expectation value of C times its dagger minus mod of C squared. This bit here is irrelevant. But if you think about what this object is, here this correlator contains something that created 3 quarks. Well, C dagger creates 3 antiquarks. So C dagger creates 3 quarks and 3 antiquarks. Right? And so you have something that might, at time 0, create 3 quarks and 3 antiquarks. And, okay, it does produce a nucleon and an antinucleon. Unfortunately, that's not the lattice state with those quantum numbers. And those 3 quarks and 3 antiquarks are quite happy to realign themselves into 3 pions. Okay, so this correlator here will be a sum of exponentials with the right quantum numbers. There will be a contribution that looks like e to the minus mass of the nucleon plus mass of an antinucleon t, but there will also be a contribution that looks like e to the minus roughly 3 times n pi t. Okay, and when I look at the noise, which is the square root of this variance, it goes like e to the minus 3 halves n pi t. And so now, the ratio of signal to noise, which is what you really want to look at, will go like e to the minus mass of the nucleon minus 3 halves mass of the pion t. And that is a positive number. For no matter what you choose for the quark masses or the number of colors, that's a positive number. And so you see that there's a problem that as you go to late times, your signal goes away. Okay? And this argument is due to Peter Lepage and from a long time ago. If you repeat the same argument for a nucleus, then instead of three quarks here, you have 3A quarks. And so in CC dagger, you produce 3A pions. And so you actually find that there's a contribution to the signal to noise that will go like e to the minus atomic number times this factor, t. Okay, and so this is exponentially worse. That's the theory of what should happen. But 5 years ago or so, we did a calculation where we looked at these effective mass plots for systems with barrier number 1, barrier number 2, and barrier number 3. And the particular system doesn't matter. What's interesting is if you look at these effective mass plots, you don't see, there's a region here in which these uncertainties are not growing with time. Okay, so the theory tells you that they should grow with time, but something's suppressing that contribution. If you look later on, you see eventually they do start growing exponentially with time. So that the argument before is not wrong, it's just that we've through a choice of how we excite the quantum numbers of this system, we've managed to suppress this particularly noisy contribution.
But you knew the argument was all asymptotic.
Yes, it is asymptotic. We didn't know when it would kick in. Okay, this is really the first calculation that went to this three nucleon system. And really, what this is telling you is that you've got more freedom than this argument just gives you, right? You have a freedom in how you excite those quantum numbers, and in this particular calculation, we were able to do it in a way that suppressed this overlap onto this particularly noisy state for long enough such that we could actually extract the energy of this with quite high precision. Yeah.
So I imagine these are anisotropic lattices.
These ones are, yes.
So in Fermi, how large is this golden window?
Well, you can see it depends on the atomic number as well.
Yeah. 2.
Sorry?
For A equal to.
Right, so the lattice spacing here, the temporal lattice spacing is about 0.03. So this is sort of 1.5 Fermi or so here. So you also notice these are very flat plateaus at the start. So these are sort of a variationally improved set of operators.
It's also happening that if you become less physical, if you increase the quark masses,
Yep.
you could actually reverse the principle of the sign.
You can't make, no, mn minus 3 halves n pi is always positive.
Because I'm going to always increase with that too.
Right, yep. So if you go to the heavy quark limit, they're both scaling linearly. So we can use, this is a little technical, there are kind of more sophisticated we can use, instead of looking at one correlation function, we can in fact construct a whole bunch of correlation functions with the same quantum numbers. And what you can do with this matrix of correlators is solve a generalized eigenvalue problem that basically allows you to optimize overlap onto the eigenstates of the system. And this is called the Lucia-Wolf method quite often. There's actually another optimization you can do to this system, and there's an optimization problem you can do that actually maximizes the ratio of signal to noise. And so this is something that Mike Indris and I worked out last year. And in principle, you can improve these signals very, very significantly. And ideally, you would do a combination of both. So this is just one quick plot. So this is the relative signal to noise ratio. So the best we can do, and this is for looking at correlators for a proton with a 5x5 matrix of correlators. The best you can do is 1, so we've in fact normalized to this, and this is using this optimization technique to produce a source and a sink that overlap least onto these noisy contributions. The straight variational method where you optimize the overlap onto the ground state gives you this signal to noise ratio, and you can see that we can do a lot better up here. This, however, introduces contamination from excited states into your signal, so you can't go to as early times as you can down here, but you can do a sort of an intermediate thing and get factors of 2 or 3 improvement in extractions of energies for these systems using this. But let me not spend too much time on that. Okay, so the other problem is this problem of combinatorics. So here, now, instead of a single proton, I've got, say, an alpha particle. So I've got 2 protons and two neutrons. Blue is up quarks and red is down quarks, I guess. And our QCD correlation function involves creation operators at this time here and annihilation operators at this time here. And in doing your functional integral, you have to do the fermionic integration, and then it really amounts to the equivalent of Wick contractions in perturbation theory. And you know that in Wick contractions, you have to do all possible permutations of how you tie things together. So in fact, this up quark here is not just contracted with this one over here, it has to be contracted with all of these other ones. Okay? And there are in fact number of up quark factorial times number of down quark factorial times number of strange quark factorial ways you can do this. And for the alpha particle, well, there's 6 up quarks, 6 down quarks, that's 6 factorial squared, which is about 500,000. So there's 500,000 different ways I can tie these things together, compared to in the proton there are 2. And so this is naively 250,000 times harder. But in fact it's not. So with Martin Savage and Kostas Organos, we worked out some sort of algorithmic trickery that lets you do these many different contractions in a way that really actually only scales, well, in the best case scales cubically in the number of protons that are in the system. And we've used this to study very large systems, so systems actually with pions, you can make it scale linearly with the number of pions. So we've studied systems of up to 72 pions and up to A equals 5 nuclei. So I just want to highlight a couple of examples. I should hurry up. So this is 2-body systems, and this is an example of a funny 2-body system involving 2 lambda baryons. So in order to understand this system, you have to be a little bit careful, because when you put multiple hadrons inside a box, determining whether you've got a bound state or not is a little complicated. You really have to study the dependence on the size of the box. But we do this, so these are 3 different volumes used in this calculation. You can see this state doesn't move, and that tells you it's a bound state. And this was really the first multi-hadron bound state that was investigated in QCD. So a whole range of different dibaryon systems have been studied, so the H dineutron system, the deuterons, and even weirder ones. And these are really something we can control. You notice these calculations are all at quite heavy pion masses, so this is the pion mass going over here, the physical value is down here, so we're nowhere near doing real world physics with these, but we're starting to get there. Let me go on to larger nuclei. So this is 3-body and 4-body systems. You can't see some of these, but these are the effective mass shifts from the free system. So the negative shift of this is really a sign of the binding, at least if you study it in multiple volumes.
So this big, the growing rigidity, this is the Lepage.
This is Lepage killing you eventually. Yep. So our optimization is not worked so well in this case. Yep. But in the end, from those shifts and doing it at multiple different volumes, you get to extract the spectrum of nuclei. Those calculations are not at the physical pion mass, they're a very heavy pion mass, 800 MeV. But you get this picture here, which you can sort of see. So these states up here correspond to 2-body systems. These ones that you can't really see are 3-body systems. And then these are 4-body systems. So helium-4 where you replace one of the neutrons with a lambda, and even helium-4 with 2 lambdas in it. So this is kind of interesting that you can do this. It really sort of opens the door for a lot of things. But it's also interesting to look at what happens here compared to the real world. So at this heavy mass you find that many more systems bind than do in the real world. So for example, the dineutron system is not bound in the real world. Okay? But at this heavy quark masses it is bound by 20 MeV. So it's interesting to think about the nuclear physics of this point.
How about the difference between up and down?
So this is UD and S are all degenerate in this calculation.
So there's also this problem. So
yep.
So it's another system, it's not QCD.
This is not the real world.
Right.
This is
not only gravity, but also the isospin. There is no isospin difference between each
Right, there's no isospin breaking. Yeah, it's very, very different place. Okay, and this is just a summary of our calculations and the PAC-CS group as well. Let me not spend time on this though. So one thing I did want to highlight is that this connection I talked about earlier of taking QCD and connecting it to other methods to go to larger nuclear systems. So this is something that's actually happening for spectroscopy at the moment. So this is a calculation of Nearby Mayer and Company, where they've taken our lattice QCD calculations of the bindings of these systems in this unphysical world where pions weigh 800 MeV, and used it to tune the 2 nucleon and 3 nucleon interactions that they need in order to do many nucleon calculations. Okay? So this is shown here. So these are the 2-body and 3-body system where they've taken our lattice QCD calculations, because in this world you don't have experiments, so you take QCD. They've tuned their interactions such that they reproduce those 3 energies. And then they can make predictions for what larger systems should be. So they can predict a 4-body system, they get that red error band which compares with our direct determination, so that's sort of a validation of what they're doing. And then they can go on, they can look at 5-body, 6-body, and using other methods that they're still developing, they can in fact go to much larger systems.
So you can ask you a question for the effective description.
Yep.
What is a small parameter there that makes it controllable? And
So-
why should I believe it?
Right, so the small expansion parameter is really the momentum of the system.
So it's like, but it's not character.
It's not chiral perturbation
You
theory.
do that, from what my understanding.
Right, so yes, so this doesn't control the mass dependent. Certainly this pionless effective field theory doesn't control the mass dependence at all. Okay. So this is
So to be taken with a grain of salt, I mean, these predictions can be easily 50% wrong.
at this mass. So the
I mean, I think that predictions. The validation, I understand why they
Yep.
did it, because
Yep.
you know, whether or not I go to even higher helium 5 or lithium 5.
Right.
I mean, so in principle, this effective theory could be 50% wrong.
Right, so
Correct.
there is a power counting this effective theory, and so they've gone to some particular order and have uncertainties that come from estimating what the next order is going to be.
Plus, the counter themselves on average of percent.
Right, so what they so this is
understand. It's
really
not,
really
I'm
the
not
tuning.
being critical. I want to understand better whether
So-
it is actually
okay.
predictive or not.
Right, so the tuning they're doing is really determining the counter terms of the theory. Right, and so once you've done that, then the uncertainties out here are really an estimate of the higher order terms they're neglecting. Okay, we can talk more about that.
No, that's okay. I
It's-
just want to know.
Okay, so now let me get to matrix elements, because this is really what I want to talk about. So this is a picture of how some external current interacts with the nucleus. So the Born approximation is really that it interacts with a single nucleon. Okay? And so that gives you a cross-section that goes like the single nucleon matrix element times the number of nucleons squared. Okay? And so this contribution here, if you're lucky, you know from experiment, if you're doing electron scattering, then this is just the matrix element of the vector current in a nucleon. If it's something you don't have such experimental control, you can ask your lattice QCD friends what that matrix element is, and that's something that we've been doing for many years. And that, at a kind of a hadronic level, that looks like this: the sum current hitting a single nucleon. Okay. However, an external current can also interact non-trivially with multiple nucleons. So I kind of have a picture where it's not interacting with this one and then that one, it's really interacting with these two sort of coherently. Okay? And that gives you a different contribution. So that gives you, as well as this term, it gives you this two-body contribution matrix on with that current with some coefficient, which you don't know. And of course there could be higher order terms here. But you know that eventually, because of the finite size of these things, the kind of importance is truncated by the size of the system.
So logically, wouldn't also this be proportional to some function of A in terms of like how many
Yeah,
pairs
yeah.
you can...
So alpha depends on
okay.
on the spin and isospin and everything of the nucleus, right, and the atomic number. Yes. Yeah, so this, naively you would say this is A choose 2. right? You choose every pair of nucleons.
Exactly.
It's probably more complicated than that. Schematically, what this really corresponds to is, for example, the current interacting with a pion that's being exchanged between these two nucleons, or some kind of local operator where the current interacts directly with two nucleons. So this is poorly known, but it can be significant. So it will certainly shift cross sections by some amount. Okay? But it's also importantly, and this is partly what you were saying, Chris, this may depend very differently on Z and A compared to this. Right? So you may have in some nuclei that this is enhanced over this, which would be very interesting. Fundamentally, if you don't know this, it leads to significant uncertainty in your predictions for the cross section. Okay? Part of what I want to stress is that this piece, you can see it's actually two nucleon physics, right? So if you know this current in a two-body system, you can actually make and understand how this depends on the atomic number. Then you can actually, even knowing this from few nucleon physics, you can make predictions for large nuclei. Okay. So this I showed earlier. This is just to remind you how badly we know these pieces. So basically, what this corresponds to, this quenching of the axial charge, which I talked about earlier, that corresponds directly to this piece here. Okay, adding that in is fixing up that missing physics. Okay, so how do we look at nuclear matrix elements? Well, again, in principle, we know how to do this in QCD. To measure a matrix element, what we do, instead of measuring this 2-point function, we take a ratio of a 3-point function to a 2-point function. So we've seen this bit before. The only difference here is that now, as well as creating our source with the right quantum numbers and annihilating it over here, we also insert some external current. Okay? And by pulling all three of these points apart in Euclidean time, you get access to the matrix element you need. Okay? This is something that we're just starting to do for light nuclei, and I don't have any results to show with this particular method, but there's another way you can get to the same physics, and this is by making use of external fields. So if you think about, say, a proton and place it in a fixed external B field, magnetic field, then that magnetic field modifies the energy of the eigenstate of that system. Right? You get the mass of the system plus some Landau level contributions, plus a spin-dependent piece that's the magnetic moment dotted into the B field. And then you get quadratic pieces in the B field, which are called polarizabilities, and then higher order pieces. Okay? But you can see that in this particular case, there's an energy of an eigenstate of that system that tells me about not just the mass of the proton, but it also tells me about the magnetic moment and these polarizabilities. Okay? So what you can do is you can measure the energies of the states of the system for a range of different background fields, so strengths of the B field, and basically fit those energies with this form here and extract the matrix element. So the magnetic moment is a matrix element of a vector current in the system. Okay? And although the example I'm going to talk about is really for a B field, there's no reason that we're constrained to use simple electromagnetic fields. We can impose axial fields or twist 2 fields, if you know what those are, and pretty much anything. So this is an example where we've actually done a calculation which came out late last year. And in this case, what we're trying to see is the magnetic moments of various different hadrons. So this is for the proton, neutron, deuteron, helium-3, and the triton. So that's P and N. And what we're looking for is the spin splitting between as a function of the B field, between the spin up and spin down pieces. So these are all spin up, sorry, this is spin 1. These are spin half systems, so we're looking for the spin half up minus spin half down energy. So that difference cancels this leading M piece, and it also, cancels this bit and just gives you the magnetic moment piece. So this difference here will go like the magnetic moment times the field strength plus some higher order stuff. Okay? So the goal is to extract this energy shift, and we do that by forming ratios. So this is this correlator of the particle with its spin up divided by with the spin down, and then this is with the field turned off. You don't need to worry about this, but it's basically directly extracting this splitting, and this ratio is shown over here, and then the bands correspond to exponential fits to these various pieces, and each of these corresponds to a different field strength. Okay, so from this data here, you get to extract the energy shift as a function of the B field strength. Okay, and this is, yeah, as I said, for one body, two body, and three body systems.
So and how this is connected to the NN, NN correlator?
Right, so here, this magnetic moment is really, so I'm really taking my, right, the magnetic moment is coming from that. So I'm not just pulling out the two-body piece, I'm really I'm measuring the whole thing. If I wanted to get the two-body piece, I would have to subtract the one-body pieces that come in as well, which I will do in a second. Okay, so yeah, this gets contributions both from one nucleon physics and from two nucleon physics and three nucleon physics in principle. Yeah.
How do you use this background field? To play with boundary conditions?
Yes, essentially, yeah, we basically take our gluon links and multiply them by an abelian phase as well. And we get to cheat a little bit here because we have up, down, and strange quarks are degenerate, and the charge matrix is traceless. So you don't have. Yeah. So you don't have to have this present during the generation of the gluon.
That's exactly my point.
Yeah.
So do you need to generate a new sample?
Not in this calculation. In the white
In the
calculation.
general case you would.
Yep. Yep. Okay.
Can this be checked experimentally, or the magnetic field that you need is completely off?
It can't be checked because of this.
Okay.
But you will see. Just wait a second. So this is these energy shifts for neutron, proton, and then the nuclei as a function of the applied B field in some units. So the data points correspond to the determinations, and then the bands correspond to our fit, and the linear term in that fit is the magnetic moment. Okay, so this lets you extract the magnetic moments. These are the magnetic moments of these nuclei, are the bands here. The red dashed lines actually correspond to the experimental determinations of measurements of these matrix of these magnetic moments. And there's a little bit of so you might remember that magnetic moments are measured in nuclear magnetons, which are E squared over 2 times the mass of the nucleon. Okay, we've actually measured them in the appropriate units for this calculation. So we measured them in E squared over the mass of the nucleon at this pion mass. Okay, so there's a scaling there. And so plotted in the sort of right units for this unphysical universe, you see that these are actually pretty similar to the magnetic moments in nature, which is not what I expected to see in this calculation. Okay, and it actually tells you something kind of interesting about this unphysical world of 800 MeV pions. So in the physical values, if you look at, say, the proton and the triton, so the triton is a PNN system, and it has in the shell model, so the simplest nuclear physics model, it has the 2 neutrons spin paired to give J equals 0. So that the magnetic moment of the whole system is really determined by the magnetic moment of the proton. And so you see the agreement in the real world between those 2 magnetic moments. And that also persists at this unphysical mass. And so it suggests at some level that in this heavy quark universe, nuclei are still shell model-like, which I think is not an obvious thing for them to be. It could be that when you go to heavy quark masses, nuclei are really just clumps of quarks.
Sorry, I appreciate that, but I mean, there's also the spin crisis and the proton that doesn't seem to be carried by the quarks.
Right, so gluons are important.
Right, so this seems to capture also the gluons?
So that's, I mean, that.
Maybe I'm wrong. I mean, that's
So there's certainly many more detailed questions that you can ask about this system. This is really the first kind of, yeah, I mean, yeah, you know, at heavy quark masses, even certainly the magnetic moment of the proton at heavy quark masses is not what it is in nature, right? And the distribution of spin between quarks and gluons will be different.
I mean, this seems to measure the, as you say, since you rescale the masses,
Yeah.
the Bohr magneton is basically just an naive scaling of that.
Yes.
It doesn't seem to
Yeah.
change
It's telling you that doing that is pretty much all you need to do. Kind of interesting in itself. All right. So let me skip that. So the last thing I want to talk about, and this is just a couple of slides, is doing this for something where the current is more interesting from a particle physics
So I
point
can
of view.
ask you again about this background maybe
Yeah.
before you go. Could one get dipole moments into it? When we talk dipole moments.
Electric dipole moments.
Yeah.
So yes. So if you did,
special background.
so this is the magnetic moment is a dipole, right? It's a magnetic dipole. But if you want an electric dipole moment, you need to have CP violation. So if you did this calculation with a theta term as well, you would be sensitive to that. But doing that, there's really a sign problem hiding there. So it's not.
I guess rather than take the question, if I understand correctly, you could imagine a world that rather than 3 colors, you have 2 colors. At
Yep.
that point, the pions are mesons,
Yep.
scalars, and for scalars you have the electric dipole moment rather than a magnetic one, which is CP even.
Yep. Yep, you could do, yeah. So in fact, so the LSD people are doing background field calculations in 4-color QCD and looking at polarizabilities, which is this. So this next order shift here, these polarizabilities are really what they're after.
I mean, we also look for this in the case of SU2, right? For that matter too.
Yep. Right.
Yeah, we have that too.
Yep.
That's actually better because those are Gaussian bosons. In SU4 they're not.
Right. Yeah, so let me just say something very quickly about scalar matrix elements. So if, for example, dark matter interacts through exchanging a scalar particle, then the QCD piece of that coupling is basically Q bar Q. So it's the scalar operator. So what you're interested in is a nuclear matrix element of Q bar Q. And this is nice because it's accessible via Feynman-Hellman theorem. So because in the Lagrangian you have a term that's NQ, Q bar Q, by taking a derivative of the mass of a system with respect to the quark masses, you get access to that matrix element. Okay? So people have used this a lot for looking at the single nucleon matrix element of Q bar Q, which is called the sigma term. But you can also do this in the nucleus. Let me just again. So these are this one-body contribution and then two-body contributions. And what you're kind of interested in is, what I'm interested in is how significant these pieces are. And in fact, in the literature, there are arguments suggesting that, in particular, this one here is enhanced relative to its naive power counting in the effective theory, because there's now, instead of just a 1 over q squared propagator here, there's in fact 2 of them, because there's no derivative here. And so this gives an enhancement to it. And so if that was the case, then this two-body physics in this particular system would be equivalent to the one-body physics. So I think this is this paper we were talking about earlier, right? So as I said, this you get to look at from understanding the quark mass dependence of the energy of a system. And so what I'm really interested in is the two-body physics. And so what I'm interested in is the difference of the nuclear matrix element of U by U plus D bar D from A times the nucleon matrix element. Okay, so this difference here from 1 is a signal of two-body physics. Okay. If you take this expression and use the Feynman-Hellman theorem, you get to rewrite this in terms of the mass derivative of the binding energy of the system. It's not the total energy of the system, but the binding energy is sensitive to this difference. So what we can then do, and have done, is take, as I showed, we've calculated binding energies of light nuclei up to A equals 4 at unphysical quark masses. So at 800 MeV I showed you results. There's also results at 400 MeV and a couple at 500 MeV. And of course, we have the results which are very precise at the physical point, just from experiments. And so we can numerically construct this derivative as a finite difference. Okay? And that lets us measure this quantity here, and that's shown down here for the deuteron, helium-3, helium-4 as a percentage. And so this is 2%, 5%, and 5%. So that is really what you would naively expect from power counting of how important these pieces should be relative to this, and is not the very large contribution that was suggested. So this is something where really these, of course this is really only in these light nuclei. So this may not be the case in a heavy nuclei where the effective theory is on a much less solid footing. So let me finish. Just so I hope I'm seeing that light nuclei is something that we can really seriously study directly from QCD. So we've been studying the spectroscopy for quite a while. So light nuclei, which, okay, not that interesting because we know what the spectrum of these is from experiment to extreme precision, but also you can ask about other systems. So you can put in lambda baryons instead of neutrons, and so there's a whole field called hypernuclear physics that is really interested in this, and so you can make predictions that are competing with experimental precision there. But beyond that, we're also now starting to look at nuclear properties and matrix elements in nuclei that are really something where we can give it information where experimentally there's nothing or just very little. And so the prospect that you can really make you can really start nuclear physics from the standard model and make controlled prediction, that I think is pretty exciting. And I think in the next 10 years that this is going to be a kind of important thing for these intensity frontier experiments in order to control their uncertainties. In the case of the magnetic moments at this heavy mass, you actually learn something somewhat interesting about nuclear physics as you try and do this. So thank you.
Question? Yeah.
Yeah. So, is there a particular interaction that you think it could lead to like large differences? Because you showed the scalar one,
yep.
Right? So, do you have any sort of like?
No, I mean I would be extremely surprised if there was anything where there was more than a 30% effect. I mean, I think this is really, I mean, it's not at the level where not knowing this two-body physics means that you either detect something or you don't. It's really at the next stage when you've detected dark matter, how do you interpret what it's doing?
But of course, like the heavier the nucleus you have, the bigger the difference, I guess, right? Because
well, I mean, certainly if you say this thing naively goes in a large nucleus goes like the number of pairs of nucleons, then yeah, for A equals 100, this is going to be huge compared to this. But it's not quite that simple because this nucleon over here and this one over here on the other side of the nucleus don't interact, don't really.
Yeah.
So there's sort of a cutoff by the range of the strong interaction that goes on.
You also written a paper, if you remember correct, there's other questions about, the possibility to export some of these to the outside model.
Yes. Yep.
Can you comment more on that?
Sure. Yeah. So what we did.
Because,
I mean, as you guys have been doing, we looked at two-color Qcd and asked the question. Well, really, from the point of view of nuclear physics, what I'm interested in from the point of view of nuclear physics is why is nuclear physics like it is? Why going from quarks and gluons, the fundamental degrees of freedom, do we really have these effective degrees of freedom of nucleons inside a nucleus? I think that's not a priori, there's no reason that should happen, right? We just have some set of quantum numbers, a blob of quarks would be equally good. So there's some level of sort of emergence of scales that's pretty interesting, and so without being able to probe that experimentally, you can do this in a numerical experiment. You can change quark masses, which I sort of showed today, but you can also change the number of colors. And so we went to two-color QCD, which is it's numerically a simpler theory to deal with, and ask the question: if you take the kind of fundamental baryons of that system, which are actually scalar particles and are degenerate with the pions of that system, so it's very, very different than real-world QCD. But if you take the fundamental baryons, which are two quark objects, and take more than one of them, what happens? Okay? And so, so you can have baryons that are Q bar QQ, so scalar ones, which are mass degenerate with the pions. And so I'm going to call those nucleons. And then you can take the analogues of rho mesons, so Q bar gamma mu Q, and the analogues are Q gamma mu gamma phi Q, so axial vector baryons. Okay? So if you take these two objects, in fact you can show that these ones, that any number of those will not bind, right? So they have to be above n times the mass of the pion. But if I take one of these and some number of those, 2, 3 or 4 or more of these, we actually showed through using these finite volume scaling techniques of Lucia that the so this system, so delta n system, which I'm going to call a deuteron, is actually below the threshold for, below the sum of the masses of this one and this one. And so is a bound state of the theory, as is the delta nn and delta nnn.
But these, if I remember correctly, the works had mass, a very large one.
They were, so the masses, so m pi over m rho in our calculation is about between 1/2 and 0.9. So these, we're not trying to do chiral,
Well, yeah,
right, because it gets very expensive.
forever. Right?
So we wanted
but
to
you
do,
expect that to exist also in the chiral line? That wasn't clear to me.
I don't know whether you, so we studied it over a range of masses, and in all cases there seem to be these bound states.
Because you also write the chiral Lagrange for this, but I don't know how much I can trust the chiral Lagrange.
You can't trust it for so many masses, right?
So basically the chiral Lagrange used for phenomenology is not really trusted.
Right.
So I was right about it.
Yes.
Okay.
Yeah. So we
I'm just trying to understand exactly.
so this spectroscopy was rigorous QCD.
Yeah, the dark matter side
Is
very
is
clear.
hand waving.
just to understand
Yes.
exactly what was the.
Yes.
Because that I liked it very much. The other part I didn't understand it because chiral perturbation theory was being used when it
Yeah.
could
So
really
I
be
mean,
used.
really, so the point of view of our phenomenology study is really that so if you have a deuteron-like object, so you can have a process where you have NP. So in the standard model, what happens if you have a neutron-proton is these bind into a deuteron by emitting a photon, right? But the interesting thing about this is, although the energy scales of these are lambda QCD, and this is sort of twice, so let's call this, there's a mass of a nucleon and this is 2nn. But the thing that the energy that's carried away here is the binding energy, and this is 2nEV instead of 2gEV. Right? So the nuclear physics of this process gets you basically a hierarchy. And so you can have, if you think about this in the dark sector, where this is not a real neutron and a proton, but is these funny objects here, the kind of nuclear synthesis process is something that's kind of new in this system, and you get a new scale out. Right? The binding energies that we find are small compared to the mass of the hadrons in this theory, over all of the masses, all of the quark masses we studied it. And so that sort of new scale you get gives you interesting phenomenological consequences.
So having assumed that the dark matter candidate is light enough, I mean, it could have been at different energy scales, so you just
right.
assume that to be in order of jets, right? Is it correct? I think so.
So it depends. I mean, really.
I'm trying to understand it. So,
Yeah, we have really no idea what energy scale we want to think about this theory at. What we did is set the scale with saying f pi was the Higgs curve. Okay, you guys did.
Oh, but in our case, it breaks it to weak, correct? I mean, so there is I mean, in our logic, I mean, that theory, in fact, has the correct properties to break electroweaks, and the pines
Yes.
cannot be mass.
Yeah,
If
we're
the pines are massive,
Right.
then electroweak cannot be broken
Right, so-
because the global symmetry are no longer there.
Yep.
So we don't know what I'm doing. From the electroweak point of view, we can always claim that there is a scale of the electroweak, and this theory can be coupled to the electroweak. And in fact, I think that's what you did
Yes.
to basic some other scalar. But there is, at this point, there's absolutely no reason to be there.
That's
It
right.
could be anything
Yeah.
from you to the Planck scale.
right.
Which is, I mean, I'm not arguing, I'm trying to understand exactly, because I did appreciate this, we missed it, I mean, in the sense when we were doing the SU2 calculations, we were always in the Carrel regime, because that's where we want to be. In that one, I don't think you can easily see these bound states that you were
I
saying.
mean, the problem with the Color regime is it becomes very expensive, right? I mean,
Right, right.
these calculations are, you have to study them for many different volumes to really see their bound states.
But on the other hand, if that model is correct and things are fine, then you can still say what you're saying, and there can be bound states, but in a more, theoretical under control theory. That's what I'm trying to understand.
You mean for likewise?
For
Yeah.
for like masses, and also that theory can also be used in fact to break the electroweak
Yeah,
correctly,
right,
rather
right.
than just being added on to it.
Yep,
So
sure. I mean, I think there's no reason that you can't have these bound states
It's
at likewise.
interesting.
So yeah, it's certainly interesting to explore that, but more expensive.
Well, it might be this one.
Are there any other questions? If not, let's thank Will again.